Scott's a nerd here. So yesterday I made multiple videos for the Atwood device. I did the traditional Atwood device where we have a mast going up and over a pulley. We did one where it was being pulled up a ramp due to a falling mast. And then in class, what we did is we did one where we had a cart being pulled by a falling mast. And we found that the formulas are all very, very similar. And this got me to thinking that there's probably an easier way of going about proving this and showing that how this works that cuts a lot of the steps out. Now, unfortunately, it does make it a lot easier to make mistakes when it comes to if a direction's positive versus negative. The way we've been doing it, the way I showed it, is the absolute proper way of doing it. But what I'm going to show you is a bit of a shortcut that should also work in most situations. And let me show you. So here's my whiteboard. So I'm going to start with Newton's second law. Now we know that Newton's second law is not F equals ma. So traditionally it's F equals ma, and that's the right mathematical formula, but it's not the right form of the formula. And those of you in my class know I've talked about this quite a bit, that the formula is in fact actually the sum of all the forces on a mass, or we can say a group of masses that are all being treated as one mass. But the sum of the forces on a mass is equal to the acceleration of that system. So this is a much more proper way of doing it. And you might already be starting to see how this might simplify matters a bit. We're going to keep this form, and what we're going to do is I'm going to just do a basic Atwood device here, and we're just going to plug in values into that formula. And you're going to find that it is a bit simpler. Now, one thing we do have to do is we do have to accept the fact that the tension here is the tension there, and that the tension becomes sort of obsolete because we know that the mass times acceleration here is the magnitude of the mass times acceleration here. As you were, the acceleration here is the magnitude of the acceleration here. The masses are, of course, different. And so if we're going up this way and coming down this way, that's how it would be. So, forgetting tension for a moment, let's just look at the forces on the box is working against each other. Okay, and the only reason we can do this with this problem is we're pretending this is a single system. Now, up will be positive and down will be negative in this situation. All right, so M1, so I'm just going to plug in for the forces. So force of gravity on 1, minus, or well, we'll do plus a force of gravity on 2 divided by the total mass, which is M1 plus M2, 2 should equal the acceleration based on the Newton's second law formula. Now let's look at the F of g. Okay, this simplifies to m1g. Okay, and this simplifies to negative m2g. And the only reason I'm saying it's negative is because the force on this side is this way, and the force on this side is that way. Okay, some of the forces. Now, you can probably already see how this is going to simplify already. So let's pull g out of the formula, out of both of those right there, put g out front, and I'm just going to rewrite m1 and m2, and you see, just using a few steps, we've ended up back at the same formula. It sort of makes sense, right? The force of mass 1 is the opposite of the force of mass 2 divided by the total mass of the system will equal its acceleration. That is a much simpler form. This also works for the sliding block situation. If you were to do this for the sliding block situation where you had the Atwood device with a pulley at the top, a mass going over the pulley, going down a ramp, and a mass here, and we'll say this is M1, this is M2. The equation would be the same, except the force here would be M2 sine of theta times that g. And that's all you would change. You would end up with the exact same situation. And of course, in a more complicated situation where you had two ramps, a ramp on this side and a ramp on this side, let's pretend this mass wasn't here, and instead there was a second mass right here, so that's our mass 1, then this would be the sine of m1 here minus the sine of m2 here, based on which those individual angles were, right? Times gravity, so those would actually become forces if we ever divided them out, that would equal the acceleration. So this actually covers every single scenario. Now, the one problem thing I don't like about this is you are basically excluding the tension forces. The tension in a real world situation will not always be the same on both sides because, like we were talking about before, if we do have a non-massless string, which in reality we always have a non-massless string, then the mass is going to be changing on each side. Therefore, the total tension, I guess the total tension will be the same, but the accelerations they'll be different to calculate. And so what we want to do is you want to include the tensions in your problem. But in the situation where we pretend it's massless and it's just a point connecting two spots together, it's easier to get to this situation if you just follow Newton's second law. All right. Well, Scott's a nerd. That's physics, and I'll see you guys later. Leave some comments if you have any questions. Thank you.